back to the next installment of the AP ECE Chemistry Chapter 17 Spontaneity Reaction Problem Set. I'm Mr. Wilkosz. Let's look at problem 43. In problem 43, you're asked to find when the delta G naught will be 0 for a specific reaction 2Cl minus plus Br2 gives Cl2 plus 2Br minus. The first thing you need to do is calculate the change in entropy, and then you have to calculate the change in enthalpy using table 17.1 and 8.3 respectively. You find that the change in the enthalpy is 91.2 kilojoules for that specific reaction using all the same tips that we had talked about in the previous screencasts. And you find that the entropy change is 0.1226 kilojoules per Kelvin for this particular reaction. You substitute into delta G naught equals delta H naught minus T delta S, and then solve for your temperature in Kelvin. So you want your G to be 0, it's like it's equilibrium, and you have a value that you just calculated for your enthalpy, and you have a value that you just calculated for your entropy, so then solve out algebraically for T, and the temperature should be 744 Kelvin. Let's check out the next problem. In problem 51, you're asked to consider sulfur, which has 20 allotropes. Commonly the ones that are dealt with are the rhombic and monoclinic ones. They have different crystal structures. You can actually write an equation to describe what happens with those. That's sulfur right here in the solid state, but the rhombic solid state in equilibrium with sulfur. That's what that S is for. In the solid state, that's what that S is for, but in the monoclinic form. You're given some information about the monoclinic sulfur. Its heat of formation is 0.30 kilojoules per mole, and its entropy, standard entropy, is 0.0326 kilojoules per mole per Kelvin. You're given those because they're not readily available. The question is, what temperature are the two forms at equilibrium? You got a decent amount of information available to you already. So what you do for this one is calculate your change in entropy first from the equation. And one of the values, the rhombic one, is available right in the table, table 71. The other one was given to you in the problem. You can find the entropy change for this. And then you can plug that entropy change into delta G naught delta H naught minus T delta S, the Gibbs free energy equation. 0 on one side because you want them to be at equilibrium. Plug in your enthalpy, plug in your entropy, solve for temperature, 375 Kelvin, similar to the last problem. Let's check out the next problem. In problem 53, it's a similar problem to the previous one. You're told that you're dealing with solid sodium, and it has an entropy, a given value of 51.2 joules per mole per Kelvin, and then gaseous sodium with an entropy of 153.6 joules per mole per Kelvin. Makes sense that it's a higher entropy because it's a more disorganized state. You're also given that gaseous sodium has a enthalpy of formation of 108.7 kilojoules per mole. They want to know what temperature will you have an equilibrium between solid and gaseous things. In other words, when will it sublime, go directly from solid to gas, if the pressure is 1 atmosphere. It's a standard pressure right there. So this is going to happen when delta G naught is 0. We're using, again, delta G naught equals delta H minus T delta S, but rearranging it, it simplifies in this particular instance to delta H equals T delta S. You can solve out and just put delta H over delta S, and then you'll get your temperature of this one when you plug in the values for those things. You have to solve out for the entropy change using the tables, but you get a temperature of 1062 Kelvin. Let's check out the next problem. Problem 57. In problem 57, you're given a reaction 2H2O liquid plus 2Cl minus aqueous gives H2 gas plus Cl2 gas, and then also 2 aqueous hydroxides. You're asked to calculate the Gibbs free energy standard value at 25 degrees Celsius. For this one, took a little bit of an alternate approach. There's a table in the back of the book that has these Gibbs values. So rather than having to go and calculate, products minus reactants for the entropy and enthalpy separately, you can just jump right in and have the Gibbs energy already there. Now that's a mole-based thing, so you do have to run your coefficients through there, but you can find your Gibbs free energy change for this one to be 422.4 kilojoules. In part B of 57, you're now dealing with calculating Gibbs free energy at a non-standard set of conditions when the pressures aren't 1 atmosphere, the concentrations aren't 1 molar. So you add this term RTLNQ on the end of it. Q is your reactant quotient, calculate as you normally would. Just plug it in at the end and you'll get a total value now of 397.9 kilojoules.